There we go. Now everything should be working fine. About damn time. So, let me minimize this out. Oh, I still have this on the wrong tab. It's fine. Oh, and memory alpha. Okay, so let me just take care of a few things here. There we go. So I'll edit all that out later. Not a big deal. Just there wasn't really anything that was personal on that previous thing. Sometimes I don't get things prepared well enough when I'm struggling trying to get something to work. Okay, so I think this time we're good. So no more interruptions. We're going to just get started. So I had oh, you know what? Shit, I almost forgot. I need to figure out what the mother. Give me like 2 seconds. I'm gonna turn the main screen off. I should have just had that off when I started, but let me go back and yeah, now that was dumb of me. Um, okay, so can I? Oh, you know what? That might work. View on YouTube. Ah, perfect, perfect, perfect. Copy link, copy link. Okay, that's there we go. Let's see if this works. Yes. Okay. So here we go, and just copy it here, and also my main channel. So there we go. So just gonna let people know that I am doing some research. Does the ROM Corruptions channel kind of have anything for that? So I'll guess put in self promo. So here, want to learn about how to corrupt TG-16 game. Here we go. There. So the three main ROM corrupting channels I'm in, my own, the RTC channel, and the ROM corrupting channel, they are all invited to watch. So let me go ahead and get this reset up and turn this guy back on. Again, I am like you know a novice when it comes to live streaming. I am not a professional live streamer. I do more standard ROM corruptions. Although I did some live streaming for the PlayStation 1, and it was okay. But I had one of my fans, and the main developer of RTC, ask me, "I'd like to see how you go about corrupting a video game, or rather, a new console." So, and one of my patrons wanted me to corrupt a TurboGrafx-16 game. So, I think the first thing whenever you're going to do a new console is you got to learn about it, and the first place to start is the basics. So, to Wikipedia we go. So this first part is going to be kind of boring if you know what the console is, but the fact is the TurboGrafx-16 was very unpopular. As I'm looking this up, was very unpopular in the United States. So here we are, TurboGrafx-16. Boom. So, I really don't know. I mean, I've got my encoder set to a relatively decent bit rate. I don't know if you can read that, but I'll try to read it out to you. So the TurboGrafx-16 was known as the PC engine in Japan, pretty popular in the Japanese market, but it flopped in the U.S. When I was a kid, I only had one friend that had one that I know of, and he was the rich kid that had everything. So of course he would have a TurboGrafx-16. Both of his parents were lawyers. His name was Brent. I kind of wonder what he's doing these days. He's probably a lawyer like his parents. So the first thing that you need to know is essentially what the hardware is. So we're going to scroll down here. So this kind of gives like the whole history and whatnot, of course. And that doesn't really concern us. We just want to know what's under the hood. Technical specifications. So the first thing that we need to look at would be the processor. So the processor uses what is called a Hudson Soft HU6280. So we're going to have to look at that really quick. if you're not familiar with Hudson Soft, they're the ones that made like the Adventure Island series, which was called I can't remember what it was based off of. Man, I can't remember, but I think they also made a lot. They were also the developers for the Mario Party series, so there was that too. So so it's an 8-bit CPU modified with two 16-bit graphics processors. So that's the funny thing. It was marketed as a 16-bit system, but the CPU was 8-bit, much like the Famicom or Nintendo, and the Super Nintendo was kind of like that too. Although it was 8-bit slash 16-bit. So, and like the Z80 is 8-bit. So technically it was an 8-bit console, but its graphical processors were apparently 16-bit, and it had two of them. If they really wanted to be silly, they could have called it a 32-bit system, because 16 times 2 is 32. Maybe they should have. maybe that would have made them a bit more popular. But it didn't look like a 32-bit system, so yeah. So the first thing that we need to do is figure out what this processor is. So because the more we learn about processor, the more we can figure out, like, if we can write code that can help with corrupting. So if you look at my Genesis corruptions, I changed the vector table so that it doesn't crash all the time. With my latest video with Magic Kingdom, I redefined the break instruction to just return from that exception. Otherwise, it would act as an NMI non-maskable interrupt, which is for the Nintendo is essentially your vertical blank. So it would keep thinking it was in vertical blank, but didn't change it. And that's something brand new that I'm going to start doing with Nintendo games. I should have done that a long time ago. I was just lazy. So, and the biggest reason why you want to do that is the break instruction is 00, and you're going to run into 00 a lot when you're ROM corrupting games. So what is this processor? Apparently, it is an 8-bit microprocessor. That is an improved version of the WD-65C02. And the 65C02 is an improved version of the processor that the Nintendo used. So think of it as a Nintendo processor, just with some added features. So we know what the processor is, so that's good. It's interesting that Hudson Soft made it, though. So we'll look at the description. That'll give us some clues, and then we're going to like go onto Google and pull up like some sort of white paper on it, so that we can kind of read a bit more into it. So it contains a 65C02 core, which has several additional instructions and a few internal peripheral functions, such as an interrupt controller. Okay, so interrupt controller. So there's probably going to be some sort of vector table, maybe, to handle interrupts. So we're going to have to learn how that works. So once we got the basic information, we're going to look at the CPU, and then we're going to try and find documentation on the TurboGrafx-16 itself and how the ROM is structured, and then we could figure out where we can go from there. But the processor is essentially step one. So it's got an interrupt controller, memory management unit. The memory management unit probably, because it's an 8-bit CPU, so it probably has a 16-bit address space. So it will probably need a memory management unit for bank switching. So I'm guessing. So it probably has that built in, where with the Nintendo, you had the memory management units on the cartridge, and that was called mappers. So the cartridge itself would have that logic, but it looks like it's built into the CPU with this one. So we'll have to look that up. A timer, 8-bit parallel I/O port, and a programmable sound generator. So that's probably just the sound hardware for the TG-16. Let's see. Slowly modified was released and used in the PC Engine, Core Graphics, and Super Graphics. I wonder if this was used for anything else. So this goes into memory mapping. So this is also very important. Has 64 KB, so 16-bit address bus. So 64 KB means that's 16-bit, because that's 65536, and that's 16-bit maximum 16-bit unsigned number. So, and a 2 2 megabyte physical address space. So that's probably how much the bank switching can go to. The bank switching can extend it out to 2 megabytes that it can read. So, of course, as it's shown here, to access this entire memory space, it uses an MMU that splits the memory space into segments of 8 kilobytes each. So, the logical address space is split as follows. So, all of it, so this is interesting because one of these addresses, one of these one of these pages is going to have to deal with things like memory and I/O, because you need to like be able to write to and from RAM, and then the rest of them could probably be for like ROM space, unless that can be swapped out. But we're gonna have to keep reading into this. Let's see. Each logical kilobyte segment is associated with one of 256 size segments. So, yes. How the hell does it handle? Okay, so the 2 special instructions are used to access these registers. Okay, so transfer the content of accumulator to an MPR register. Okay, so I think I understand how that works. Transfer an MPR register into the accumulator. Okay, so those are important instructions. So those instructions deal exclusively with bank switching, which is actually kind of cool, because if you ever look at bank switching on the Nintendo, it's a pain in the ass, especially MMC1, where it uses a serial interface, and that sucks. So that's actually pretty cool that it's actually built into the CPU architecture itself. So that's nice. Okay, so sound generator. Okay, so that doesn't tell me much. So I think the one thing about this processor that's making me scratch my head is you've got this whole 16-bit address space, but what do you do with the address space for RAM and the address space for hardware I/O? So you're going to have to control the graphical processors in some way. So you're going to have to write things to memory mapped registers for the GPU. The sound generator, I'm not too terribly concerned about that. It's got 6 sound channels: waveform playback, white noise generation, and it's got maybe a rudimentary frequency modulation channel, which is interesting. I don't know if there are specific CPU instructions that deal with the PSG. We're going to have to look into that a little bit more. So, I guess the next step is to look at the documentation. So, that will be the fun part. So, oh, this is just another wiki. Oh, that's nice. Lovely. So, it's a modified, yeah. So it looks like it has instructions to more efficiently write predefined values for the VDC, and that should be the video display controller, which makes sense. We don't have to deal with this too much, I don't think, but we do have to pay attention to this. So unlike the Nintendo, and a lot of consoles of this era are like this. The Nintendo's kind of the exception, but it's got the video memory built in. Now, the Nintendo had video memory of its own, but its character memory was on cartridge. So it was either ROM, which had predefined tile graphics, or it had RAM, where you could just write whatever to it. Both have their pros and cons, but basically, yeah. So, 64 simultaneous sprites. I think the Nintendo had about the same, or could do more. I think it was about 64. 64 KB of RAM. So that's, again, so from 0000 to FFFF. Yeah, I'm looking at the chat here. It's like, yeah, there's also character RAM, but that was slow. Yeah, it was slow to write to character RAM. But it had advantages like you could use compression and things like that. So chances are so that's the next thing I want to point out. Chances are with this processor or with this platform, we're going to run into a lot of compressed graphics for the TurboGrafx-16, which will make this a little bit more difficult. So, Rare was known for using character. Yeah. One of these days, someone's going to recommend Battletoads, and I'm going to curse under my breath because it used extensive amounts of compressed RAM. If I could find a decent disassembly, I can probably get away with just reading the disassembly and figuring it out that way. So, so the interface. So this looks. Wait, what the fuck is this? Map to FF. Oh wait, this is the that's right. This is the graphics processor. Duh. Interesting. So these are the graphical. So these are graphical status registers. I don't know what they mean by map to FF. Let me see here. Again, I don't think we're too concerned with how the internals of the GPU work. I think we're more concerned with CPU behavior, but it's kind of interesting, to read up on this. Now, figuring out how the TurboGrafx-16 video works it will be important for how we're going to scale our videos in the future. So, I don't know if they have that here at all. Because I was reading that I think this has 2 video modes, and if it does, that's going to make things a bit more difficult. But I think most games are going to use the standard video mode. That's the same, I believe, for the Nintendo. So so it's going to use an 8 to 7 pixel aspect ratio. So that'll make things simple because a lot of my tools kind of go based off of that. So let's see, what else? Sprite attribute table, patents, patent for displaying. I don't care about patents. I really don't give 5 shits about patents. I need to kind of know the technical things here. I mean, I could spend all day reading up on this, but that would be boring, wouldn't it? Okay, so let's get out of here really quick. Okay, so internal memory management timer. Yeah, that's what we were told. Memory map. Okay, so again, I would like to know exactly how RAM and hardware mapped registers work here, because it has yet to tell me. So that's kind of annoying. Okay. 16-bit logical addresses. Right. Still doesn't tell me shit about that. Alright, so this was technically not... Oh, instruction set. So, that shows it's very much a 6502 based thing. So that's like addition. These are branch instructions. Clear, interrupt, disable. So you can do a compare with an index register. So that's kind of interesting. All of this is more or less. I don't know what that one is. Store number 0. So some of these, I'm actually kind of curious about that. Writes the immediate value to the physical address. So, see, that's even more confusing. So, I guess, how the fuck does the... I honestly don't know how the addressing in this works. Okay, I mean, I kind of do. So, man, this is, let me look at this again. So this whole architecture is kind of fucky, the more I read into it. So essentially, all of these NPRs can be any sort of logical block. So this hurts. Okay, so because so this is 1FE. You got to do some weird math. Let's see, very small differences. Yeah, very small differences with 6502. But this one, the way that its banking works is very strange. So physical address equals logical address, and okay, or so yeah, that's very strange. I'm gonna have to look into that more. So let me think here. So if you were okay, so if you were to take, so let's see here. I'm trying to think here. So it's like 8. So it's in 8 different banks. So if you were to take, let me switch this over to. Oh, this should no, not grab. Okay, so if you were to take 1F, so times 8, right? That makes sense. Okay, so I believe that one of those things, one of those banks would have to have their bank switch set to probably FF. So I'm guessing from what I can tell here, and this is the first time I've looked at this, how addressing works on here. I believe like the things like RAM and things like hardware registers, what have you. So are probably stored in probably the 2 last banks. So FE and FF. FE is probably RAM. FF is probably registers, I guess. I suppose that's kind of what I'm guessing here. But I haven't really gotten to registers yet. But if I had to guess, that's probably how it works. So we learned something from the instruction set. So the instruction set has some shortcuts to deal directly with the video display processor. So that's kind of cool. Let's see. Yeah, it's got a few of those. So you've got ST0, ST1, and ST2. So those are specific to that processor. Again, kind of cool. So they designed the processor with the graphical coprocessor in mind. So very much. So this is going to write the immediate value to the. Okay, so the immediate value is just some sort of value. Okay, so that makes sense. So that goes to here, and then the next one goes to 1FE002. I wonder what 1FE001 is. Maybe this is a 16-bit operand, but these are all 2-byte instructions. So I don't know what E001 would be. It's kind of weird. But I haven't looked at memory mapped address registers yet, so we're still kind of learning about this. Okay, what other weird shit is there? Transfer. Yeah, I think these are 65CO2 based instructions where you can actually transfer and decrement at the same time. Not anything that we're too terribly concerned about. What we're concerned about is break. So break is the same instruction that we were dealing with the Nintendo. So that's probably going to be 00. Yeah, it's opcode 00. So we're going to have to find the break vector for the TurboGrafx-16 and have it RTI out. So and that will be and I think that will cause less crashing, I suppose. So something to keep in mind. With that said, Um, hmm. So are there any other instructions here that we have to worry about? So we've got, where's break again? Where the fuck are you? There you are. Break. So that is something that we need to worry about. Branch always, branch on plus, branch not equal. Branch, clear, compare, clear, compare, change. What the fuck is a change speed high? That could cause some craziness. Oh, set CPU to high speed mode. So yeah, it'll be interesting if we corrupt and hit like change speed high or change speed low. Honestly, they should have made that one instruction and do like a change speed toggle, and that would have saved an extra opcode. But whatever. Because it's one of honestly well, I think a toggle would have worked a bit better in that regard, because you're either going to be high or low, So, but you would have to figure out a way to be aware of that. So maybe it does make sense to have them as two separate instructions. I am not a hardware designer, I don't design things like that. Still, interesting instruction. I've never seen an instruction that can change the clock speed of a processor like that. It's kind of different. So, but we can't really do much with that unless we corrupt with specific bytes in mind, and I don't do that. So, although I think I don't know how to say that guy's name, but basically Urklaz, Urklazar or Urkluzar. I don't know if that U is an U sound or schwa. He probably knows. But this was his idea. So if he's watching this, if he wants to create a custom opcode list for our time corruptions. Oh, hello, P shooter. We're talking about TurboGrafx-16 instructions. Come join us. So if he wants, so his RTC, his methods are a lot more targeted. So he might want to build like an ideal opcode list and avoid things like change speed high and change speed low, because or maybe he does want them. So so we've got some bitwise operators, exclusive OR, increment, jump, load and store instructions, bit shifting. No operation is probably going to be 60. Oh, I'm sorry, it's EA. 60 is something else. 60 is RTS, that's right. My mistake. You'd think I would memorize 6502 by now, but I haven't. I got push and pull instructions, so that's typical of 6502. Reset memory bit. Fuck is that? I think that's a 65C02 instruction. Reads the 0 page address. Yeah. I was actually watching a video on the SBC 700 by Retro Mechanics Explained, which is a channel that I like. I used to be part of the Discord community, and then we got into an argument, and they banned me. So I'm a little. I wouldn't say salty, but a little annoyed by that. But I still watch the content. I'm not that upset over it. Okay, reads. Yeah, that's. So it clears. So you probably have. So if you have, where was that? So you probably have an SMBI somewhere. Yeah, there it is. Set memory bit. So in 0 page you can set and unset memory bits, and that's good for things like flags. If you have flags for certain things, so that makes sense. So you have more rotating. So those are handy instructions. So swap, so SAX, return from interrupt and return. So return from subroutine, I believe, is 60 if I recall correctly here. Yep. Yeah, I just had them confused. I'm going to close these tabs out. Okay, so what else? Store. So this was, so we were reading about that earlier. Store accumulator, STA. So those are just store instructions. Transfer, ultimate increment. Those are more transferring instructions. Transfer accumulator. This is the bank switching instruction. Again, pretty cool that they have that built into the processor. So I like that. Transfer increment none. A lot of these transfer instructions I'd probably have to read up on if I ever need to reverse engineer like a decompression routine, because chances are it's going to use things like the what was that other one that was like something DD? Can't find it. It's somewhere. I'm pretty sure. No. I'll look for it later. Set T flag, set memory bit. So that's mostly everything. So that's kind of cool. Test and reset memory bits. So it's got a few extra things. Retro game mechanics is trash. Okay, actually, I'm genuinely curious about that. So I think his videos are great. Of course, you know, I am a bit of an asshole online, so I tend to get in a lot of trouble in some servers, and I'll get kicked out of them. I'm not happy with that. Because I am someone that really likes the that really likes that sort of community. But you know, I understand that I'm not for everyone. So you know, if they want to kick me out, that's their prerogative. Fuck it. You know, it's not the end of the world. So yeah, no, but I'm generally curious why you think that's trash, because aside from the drama that happened in the Discord with me, I cannot figure out what's bad about them in terms of the content itself. So feel free to enlighten me in the chat. I'm genuinely curious at this point. So with that said, let's keep going here. So we got a timer. So you probably have some sort of okay. Now, so we're getting a little bit more information here. So the timer's IRQ vector is located at logical address FFFA. So what that tells me is, regardless of what the MPR is set to, it's hard-coded to always be the address FFFA. So that makes things a little bit interesting, because that means that throughout the entire ROM, that it's always going to have vectors at the end of each bank, because banks are apparently not fixed at all in this. Any of these, 2K banks, or is it 4K? Hold on, I can't remember. Fuck. You know what? I can figure this out really quick. 8K banks. Mostly how I feel about their content and how they're much more popular than. That's just jealousy, man. I get it. I understand. But that would be like me saying that Vine sauce is absolute trash. I don't think they're trash. Although I feel as though Vinny Vine sauce kind of maybe takes a little bit too much credit, because he takes stockpiles from other people who actually did the work, and then he just plays through them. But he's just popular, so if you want to see your stockpiles get shown, you kind of have to do it through him. But I think he gets a bit more credit than he should. But I digress. I mean, personally, I wish I had an audience that large. So we're still kind of going over the basics. So we're looking at how the address space works. We're looking at instructions. So another thing that I want to point out is this full instruction set here, I'm going to assume is going to give us an opcode chart, or an opcode graph, or an opcode table. That's what I was trying to say. Oh no, this just goes over everything. We'll look at an opcode table later. Maybe the quick instruction set list is what we would want. No. Okay, that's fine. So let's keep going. So we learned something very important. We learned that there are vectors, and it is logical address vectors, which would make sense because you wouldn't want it to be on a physical address, because if it was on a physical address and you had an interrupt and you didn't have your physical address mapped anywhere, you'd be in trouble. So it would make sense that it's at an actual logical address. So we got to figure out what all of those are, and then that way we'll be able to figure that out. So that gives us a little bit. If we keep scrolling down, I'm pretty sure we'll find pin assignments we don't care about. We're not dealing with physical hardware. We're dealing with emulators. More patentable. I don't. Okay, can. Oh, and the rest is just patents. Okay, so that tells me fuck all. Okay, but that gives us a little bit of information about how it works. But let's go ahead and take a look at an opcode table, because this is something that. So okay, just really quick, I did some preliminary. I did some preliminary research. You know, the first time someone says, "Hey, can you do this console or this handheld?" You know, I'm gonna like look it up really quick first and like get an idea of just kind of how it works. You know, but so I've done this before, but I feel it's worth mentioning. If we look at the oh wait, I'm sorry. Our systems have detected unusual traffic. Yeah, can your systems detect this? Okay, I'm not a robot. Oh, you guys get to watch me do a captcha. That's fun. Yeah, that's probably all of them. These are the just new images. You fucking asshole. Okay. Gotta be. For really, jerks. Oh my god. Leave me alone. Okay. I don't see anything here. Thank you. Okay, so it's probably because I have been private browsing enabled, just because I don't want anything personal showing up on here. I try to keep all that separate. So opcode table. So opcode matrix from Chris Covell. So he's kind of a well-known guy. So hold on one second. Give me So this is actually this is different than what I thought. So this is actually kind of interesting. So as you can see, does it show my it shows my my cursor. So as you can see, like with 33, 63, E2, and anything ending in B, 5C, DC, and FC, those are invalid instructions. So I think my next question would be did they add anything to catch an illegal operation? So for those that don't know, 6502 based processors are so simplistic, they have no logic for catching an illegal operation. The 68K does, which is used in the Genesis, and that's why I have my own code to catch the illegal instruction, and then do nothing, and then just go back to normal operation. That's why my Genesis scriptions are a lot better than other people's, because I've coded it to where it cannot crash in that manner. It can crash and soft log in other ways, obviously, but if it runs into illegal instruction, it's like, oh, whatever, and then just keeps going. It treats it as a no operation. A no operation that takes several cycles, obviously, but a no operation nonetheless. So, I can't believe Hudson would make bees. Wow. Oh my god. That I I will say this. That's a very good joke. That caught me off guard. Uh, so just as a heads up, Hudson Soft's a Japanese company, and they probably don't call it a B in uh, I can't believe you're translate.google.com. Well, it would probably help if I didn't have. There we go. So a B in English. So in Japanese. So let's see if that's a loan word. So a B is hachi. So that probably wasn't on purpose. Because they have a completely different word for it. So let's see here. I take advantage of 68,000 invalid instructions for music modifiers and ripping purposes. I'd like to know how you do that because I'm trying to figure out how you would use. I guess you would just point the invalid instruction to some sort of routine for music ripping purposes. Feel free to make a video about it. I'd be interested in it. Okay, so as I was saying before, the 6502 has no logic to catch illegal instructions. It'll just do some bullshit. Usually it's like a 2 or 3 byte no operation instruction or something along those lines, or maybe it'll do some sort of it's called an unofficial opcode where it actually does something. Sometimes it's useful. There are some games out there that are notorious for exploiting these unofficial instructions. You're not supposed to do that because the hardware could always have a new revision that changes the behavior of those instructions, and then your game breaks. So yeah. I'm still kind of laughing over the fact that there are no B's and no B instructions in a Hudson chip. That's pretty funny. So what we've got to figure out is, the next thing that we're going to do is we need to figure out what the vectors are. So let's close this out, go back to the wiki. Let's look up this really quick and see what it tells us. So here's some documents. So this is all just bullshit. So this is going to be, let's go back. Let's look up illegal instruction and see what it tells us, because apparently they have them. A classic example, SNES mini DMA bug. You're gonna have to tell me what that is, because if it deals with illegal instructions, here's the thing: the 65C816 doesn't have illegal instructions. Last I checked, I think they use the entire 8-bit opcode space. I believe. I could be wrong. Oh, you're talking about different revisions. I'm sorry. So yeah, so when there's like a different revision, it can change the behavior of something that some games rely on. So that's what you're talking about. Gotcha. Okay. So this is instruction encoding in a C thing. So I'm going to look at this really quick. This is not what I'm looking for, but this might give me a hint on what happens. Instruction table for the 6502 with illegal instructions. So it might be that whatever instructions are illegal in the 6502 applies to this process as well. Which are supported by DTV. No, illegal opcodes which contain more sub-instructions are not enlisted. Yeah, this doesn't really tell us the behavior of that, so no, that's not going to work. That's NesDev Wiki. Yeah, you see, the 6280, relatively speaking, is not a popular CPU. Like the 6502 was in everything. It was in So the Nintendo was based off it. A lot of early computers, including like the Apple II, used the 6502. A lot of other machines, arcade boards, etc., all use 6502. So it's heavily documented. The 6280 was only used in a few things. So, fuck. Let me think here. So, my initial thought is that illegal instructions are handled the same way as the 6502 or 65C02. So there's not going to be a vector for exception handling for illegal instructions. Certain games relied on sending a DMA bug, and the later version of the SNES model was released, and the games crashed. Sounds about right. That's why you don't want to. That's why you don't want to rely on hardware quirks to program your games. Lesson learned. So, okay. Let's see if we can find a manual, because the manual will tell us like a lot more. All right, here's the developer documentation. So, CD-ROM system? I don't want the. Hold on. Click. Here we are. Ooh. Okay. This is the good stuff right here. White papers. So this looks like how to use the software to code. I want like, fucking hell. I want the actual. I mean, it's cool, but creating character data. And that's more CD bullshit. Issue music. Yeah, so that's all. That all sucks. So. Tech notes. How about this? Displaying a time gauge, displaying status line, displaying Japanese characters. That's some specific shit. System outline. It's probably nothing. Nope. It's like, guys, I need. Okay, so that's the video display controller manual. Oh, hey, here we are. Probably would help if I read further down. Okay, so this is the 8-bit microprocessor hardware manual. So this should tell us exactly how these things work. This is the good shit right here. The mapping register, memory space, interrupt and break. So this is what we need to look at to kind of figure out exactly what we need to pay attention to, and what we may need to change in the ROM to figure out exactly how to corrupt like a standard TurboGrafx-16 game. So this is what we need. The instruction map is something else that I want to kind of look at too, which is kind of back here, I think, because okay, so this kind of confirms what that other table showed us. We can kind of see here that there are, you know, can I zoom in? Yeah, I can. There we go. Okay, so and then we're just going to like move it like this. Okay, so you can kind of see. Oh, that's kind of painful to look at. So, but you can kind of tell that it's, you know, 0, 1, 2, 3, 4, 5. I don't know why they have that in binary. That's kind of annoying, but whatever. Wait, hold on. They have this in a really weird. They have this in a really weird thing. So, 1, 1, 1. Wait a second. So Chris Corvell's map, I think, is wrong, because if you look. This whole line right here, if you follow the lines here, so, oh my god. Okay, so yeah, so it's actually F0 through FF, because look, 1 1 1. I'm sorry, 1 1, 1, 1. You see that? It's like a bit reversed. So it's I'm sorry. It's my mistake. I had my nibbles mixed up. So it's 0F, 1F, 2F, 3F, 4F, 5F, 6F, 7F, not C. So fucking strange. But his opcode his opcode list is all fucked up. So that's really fucking annoying. Okay, that whatever. So man, they had this like I don't like how they had this organized. It's not a big deal, but it still kind of tells us a few things. So you have break. So, and that's kind of like a 2-byte instruction, I think. But at least that tells us that. So whenever Urklazar sees this, you're gonna have to realize that that this is like 0, 1, and then it's like 3, 2, and then it's like 4, 5, 6. Then it's like 7, 6, 7, and then it's like yeah, it's all like reversed. So you're gonna so if he's watching this, he's gonna have to pay extra attention to how this is set up, and you're gonna have to actually follow how the nibbles work, and that is I kind of wonder if let's go back to opcode opcode list. Where was that opcode matrix? So I wonder if he knows, because that's BBR 0, 1, 2. So if we look at this, so if we find the, so it's, oh, I'm sorry, I'm an idiot. That's 1011. 1111 is this. I'm a moron. Whoops. I cannot math correctly. So 8. So I think he did have it right. I take that back. So it's 8, 9, A, B. Yeah, it's B. Yeah, I need to. Whoops. I need to read this better. So yeah, no, he did have it right. For some reason, I was thinking this was 1. I don't know why. As I mentioned before, I'm a moron. But that's still fucking confusing as all hell. Why is it so fucking backwards? Because this is like 8. Like right here is all the way at the end here. So they probably did this for a reason, but still confusing. But as you can see, there are supposedly illegal instructions in this processor as well. So I thought it was all filled out, but I was wrong. So let's go back to the is there a way to, oh hey, this might work. Can I double page this? Guys, double page? 2-page view? You're not gonna let me 2-page view it? Oh, it is in 2-page view. Okay, so that was my mistake. So let's look at interrupt and break. So that's going to be so we'll look at that really quick. So that's going to be like 12ish. So that's the, actually we need to look at memory space really quick. So why is this bottom top instead of top bottom? It's like, what the fuck is wrong with you guys? Okay. 64 kilobytes of logical address space is essentially on the last bank, which makes sense. So that's the physical address. Okay. Why is FF mapped to 0? That's annoying. Jesus Christ. I'll have to look at that later. Okay, let me keep looking through here. Okay, so you have an NMI. Okay, that makes sense. You have interrupt requests. So, But where's break? So, okay. Priority of interrupts. Yeah, so you have reset, NMI, break instruction. I don't like how it has an S at the end here, which is making me think that there's more than one break instruction. Is there? Let me see. There's just one, and that's 00. That's why we need to. That's why we need to redefine it, because we're going to hit 00 a lot when we're corrupting, usually, because that's usually how, and like the end of banks are usually filled with like 00s, yeah. So, okay. But why does it not show here? How are breaks handled? Organization of interrupt request register. Huh. Okay. Interesting. I'm still wondering how breaks. Hey, there we are. Break. Break is a pseudo interrupt, which is caused by software. Exactly. It occurs unconditionally whenever a break instruction is executed. So, okay. If an interrupt is caused by a break instruction, the value of the program counter is pushed into the stack +2. So, and the instruction is started at, so that break +2 is an instruction code and restarts processing. So break is, oh, for fuck. I was hoping I could highlight that, but it's trying to get it to switch pages, which is bullshit. So break works the same way in works in the same way as in the 6502. So system reset. So it looks like that's internal states after. So when a reset happens, all of this happens, but that doesn't really apply to us. So we figured out how break works, and the logical, not the physical, but the logical vector for that is FFF6. So at the end of each bank in a game, you're going to have to find FFF6 and change it to something like and have it point to what we would call byte 40, and I'm pretty sure it's byte 40. Let's see here. 40 is RTI. So RTI is going to return from that interrupt, because RTI is because interrupts push both the program counter and the status register to the stack. So you have to use RTI instead of RTS to make sure that the stack goes to the pops back to the right place. So that's important. That's why it has a separate instruction, because it has to pop two things instead of just one. So that's important. Let's see. So what I would like to know is there anything here? So I don't know if this documentation is going to tell us much about how illegal instructions are handled, but I really would like to know if it goes over this. So I'm going to look at the table of contents here: accumulator, registers, program counter, stack pointer, stack register, and special registers, mapping register, memory space, interrupts, system reset, I/O, instruction map, and instruction set summary. Excuse me, I've got something in my eye here. So I think once we figure out how instructions are handled, then we can we can probably end it there, because the next part will entail preparing the ROM for like break mitigation, and that will be a pain in the ass. So I want to do another live stream for that. So we know that we just have interrupts and reset and break for the vector table. So if we go back, one thing that kind of bothered me about that though is it didn't really show. So we got in the vector table, it didn't really show break. So it says break instruction in parentheses. No shit. Okay, so just name for IRQ1, timer interrupt, MI. So I think all of these are just like hardware-based interrupts that we don't really have any control over. So it just happens during like horizontal interrupt or vertical interrupt. We'll have to look at TurboGrafx-16 like more specific instruction, more specific documentation for that on how it handles timer interrupts and everything. So yeah. So they're probably not software based. So or at least I don't think one of those is going to be an NMI. So actually NMI has its own interrupt, and that's usually tied to vertical blank. So I think, but probably something we don't have to worry about. Let's see here. Hold on. I'm just kind of reading up on this. So I want to find how it handles illegal instructions, because that is something that I want to find out more about. Because depending on how it works, it could treat it as a no operation, which would be the best case scenario. Could treat it as a reset. Who knows? So I think that's the thing that we need to figure out next. But let's look at the software manual and see if that helps us any. Okay, so this probably will at least tell us what the behavior is for illegal operations, hopefully. So that's addressing modes, mnemonics. Those are the instructions, test instructions, control instructions. So okay. So these are all the these are all the instructions that these are all standard instructions. This tells you exactly everything that happens. That's nice. I like that. I like that. So if I ever need to, I want to download the software manual at some point if I ever need to reverse engineer for like compressed graphics or something. I think it'll be very useful. Okay. Pretty standard stuff. I'm just wondering if it's going to have any like index or oh, that's complicated. Do you guys see the typo there at the top? You can tell that this is done by a Japanese company because they've got the RL confusion. It's transfer Brock data. Brock from Pokemon. Sorry, I thought I couldn't help myself. Yeah. Someone should have gotten a native English speaker to proofread through this. See, it's block data here. So they have it right there, but if you go back a few pages, it's Brock here. So I tutor Japanese students, and they have a hard time with RNL just because of how their language works, and I usually have to correct them on that with their speech. I usually have to tell them R's with the front of the tongue, L's with the front of the tongue, R's with the back of the tongue. So Yeah. Sorry, that's just hilarious. Uh, anything on? God damn it. So, I, th- I, I don't think. Unfortunately, there's nothing here that indicates illegal instructions. I mean, I guess it wouldn't be in the official documentation, but you would think that there would be a mention of it saying if you accidentally hit an illegal instruction, this is what you would expect. It's not recommended to use illegal instructions, or it would just treat it as a no operation. Um, I'm actually kind of curious about this. Huh. So how do the PSG registers work? Hmm. So it's like, how do you access those registers? Oh, that's helpful. That it actually gives you notes for the frequencies. It's kind of them. Hmm. But it doesn't tell you how to access the registers. I don't think. Huh. Cool. Okay. So that is the big question. So we got an opcode matrix. Hardware overview. Hmm. Interesting. So we still need to figure that out. So we'll look this up again and see if we can find some. See if we could find some sort of. Okay, we need to include the name of the processor in here, obviously. We might get some info here because it does mention the 6280 here. So, see, CMOS variants of the 6502 handled them completely differently, and later CPUs in the same family were free to implement new instructions in place of the unused ones. Okay, cool. But how does the 6280 handle them? That's what I want to know. Yeah. So, yeah. So, yeah, that just tells programming with unofficial opcodes. Yeah, but I need to find some better documentation here. Let's look at this one really quick. Find. Yeah, this is the same bullshit that was in the other one here. Fuck you. Okay, that doesn't work. Uh, oh, that's an assembler. Okay. So, roll commands, macros. Let me look up illegal. Hmm. Okay. That doesn't really help me much. Damn it. Why is this so hard to find? It would be really nice to know. Excuse me. It'd be really nice to know how the 6280 handles illegal opcodes. Let me look at this one. Hmm. This is just another assembler. I don't think this will really help all that much, unfortunately. No. Yeah, go and do various things. You could always go back and look through this again. And for anyone else watching, you'd always skip ahead. Let's look up 6280. Okay. So, how are legal instructions handled? Oh, okay. That's nice. So that doesn't really. So, how are so it doesn't really tell it. So I guess with this code, it just returns illegal. I guess. So, so I guess at the end is going to just return a state name, and then the emulator or whatever will handle it in its own special way. So whatever. Okay, that's not going to help us. So come on, you motherfuckers. Give me what I need. That's 6510. I mean, okay. But what about the 6... Let's look at this. No, all that's blank. What? I get it, but damn it. Whoa! I don't know what the hell that. I think one of those websites got hacked. And with an in private window, I don't have no script. I'll have to look at that later with no script and figure out what the hell happened. Let's look at this. Yeah, this is specifically for 6502. Like 6502, like illegal and unofficial instructions are heavily documented, down to like what the logic does in the chip that But I cannot find, and I'm probably going to like kill the stream here in a bit, just because I'm probably going to have to look for this on my own, because I'm running into dead ends here. Let me try unofficial, because that's also what it's called. Okay. This might help. This might tell me what I need to know. Oh, this might actually be very handy for things like how interrupts are connected. So you have the timer. IRQ1 is for VDC, and IRQ2 is external. I think I heard that there were expansion ports at some point, so that's probably why. So okay, interesting. Okay. Let's see. How to read instructions. Exhaustive list of instructions. Okay. I mean, that's great, I guess. Not quite what we want. What about unofficial instructions? That's addressing modes. Emulator design, programming language, philosophy, appendix. Yeah, it doesn't tell us ever. So let me do a search for like illegal, unofficial. Oh, unofficial PC engine reference. Yeah, so um, we should put unofficial in things as well. That is 6280. Find. Yeah, it's. I'm gonna try one or two more things, and I'm just gonna give up for the time being. So, because this does not. Well, it's based off the 65CO2. That might help us out with that, because find maybe I want to say. I might try that. So maybe okay. So this is for the old Apple computers, but it looks like the 65CO2 converted illegal instructions to nopes. So if the Hudson Soft basically, and I'm gonna have to find like a TurboGrafx-16 emulator with a debugger and just kind of break anywhere and just put an illegal opcode in there on purpose and see what it does, and it'll probably just do a nope. So that is what I will probably do. So if we put illegal, so if it's based off the 65CO2, it probably, let me see here. So let's look at two of these things here. So here, so as you can see, remember how it's just how everything that ends in B is like an illegal instruction. It shows in the 65CO2 that any illegal instruction is treated more or less as a no instruction. So although some of the unofficial opcodes kind of do weird things, if I had to guess, I'm going to say that the Hudson processor is going to treat any undefined opcode as a no operation. So I think I'll do it. So what have we learned? So first off, we have learned that the address space in the processor is kind of weird. So it has 8 switchable banks in a 16-bit address bus. So 8 banks of 8K each. So we learned that. We have learned that the vector table is similar to that of the Nintendo, so we don't really want to worry about interrupt vectors. because interrupt vectors are going to be used by the game for various things, so you don't want to fuck with that. You do want to fuck with break, because chances are unless they use break for something, for some weird reason, we can define break as returning from an interrupt, and that will cause less resets or less other weird shit to happen. So that's probably the only vector we need to worry about. Next up, we're going to look at the game that I'm going to corrupt, figure out look at the banks and figure out, actually, we're going to look at how the ROM is structured, then look at the banks, and then see if there's like anything regarding headers or anything like that. I get the feeling that, given the fact that mappers are very much pre-programmed into the CPU, and that the CPU has a memory controller built in, that there's going to be no header information or anything like that to worry about. And that might make things a little bit more interesting, but I'm going to have to look into that later. But I think part one, I think we've gotten enough info to kind of figure out how we should move forward. So I think part two will be figuring out how the ROM is constructed and messing around with the vectors there. So I think that should about do it. So I need to go ahead and stop this. So see you guys next time.